There isn't anything unique to HVAC engineering in question 12. All the analysis could be done by those who've had a standard thermodynamics course. It's a great example of testing reading comprehension and attention to detail. The temptation is to make the question more difficult than it actually is. Initial critical thought solution elements. 1. What are you solving for? Feet of head at a particular point in a fluid piping system. 2. What is the fundamental process? Determining which elements of the piping system add pressure and which reduce pressure. 3. What are the first considerations to find the solution in connection to the fundamental process? Carefully reading the setup and identifying the elements of the system associated with head. 4. Are there key assumptions? Adiabatic steady flow conditions with no compression and useless data in the question. This video is brought to you by ExOverZero, which offers the best HVAC PE study material possible. Want to pass the test? Buy the books. Use the link below to purchase. The question speaks of wastewater and absorption chillers. It uses a fairly elaborate diagram, and it gives the volumetric flow as 450 gallons per minute. The fact that the water being pumped happens to be wastewater, and that the water is eventually being pumped into an absorption chiller are insignificant. The analysis is for water at the suction inlet of a pump. Most of the information on the diagram is redundant with what was already said in the question. But that 450 GPM flow rate is interesting and a tempting place to start on the solution path. The question should be solved for feet of head, specifically net positive suction head. And because it's a piping system, you should be thinking Bernoulli. If this question doesn't get you immediately thinking of pressure heads, velocity heads, altitude heads, and friction heads, you need to take a step back from your studies and recognize you're missing some very critical and fundamental areas of knowledge. This is Fluid Mechanics 101. You should know this. Back to that interesting 450 GPM flow. It indicates the necessary data for finding the velocity head. It's unnecessary to go through the whole conversion process, but converting the volumetric flow of water to velocity is obviously possible if the dimensions of the pipe are given, which they are. And if the velocity is known, the velocity head is easily calculated using the gravitational constant. But the question arises, is the velocity head really needed for this question? The equation for the NPSH is found in the NCEES Mechanical Reference Handbook, section 3.7.4. But in that section there are 3 different NPSHs: required, available, and existing conditions. Only available and existing conditions have equations given. Available doesn't use velocity head, but existing conditions does use velocity head. Understanding velocity head will give clues to know which equation to use. Using a casual, critical thought way of conceiving it, consider this. From beginning physics studies, you know that velocity is speed and direction. Given a constant speed and constant direction, the forceful and accelerating effects are not present. It's useful to think of head as a type of this forceful acceleration. The acceleration of altitude head comes from gravitational acceleration. The acceleration of pressure head comes from the Newtonian idea of F equals ma in the forms of pounds of force. And friction head is that classic physics concept of acceleration being a form of slowing. There's no change in the speed of the water's flow through the pipes. It's steady flow. So the acceleration associated with the velocity head could only then be a change in direction. What would cause a change in direction? Various entrances, exits, bends, elbows, gates, valves, strainers, and fittings. For example, a sharp-edged pipe fitting will cause directional change, like this. All the other things, like elbows and valves, do obvious things to the flow which slow or change its direction. The question specifically says there are none of these things. To quote Cameron Hydraulic Data, the velocity head energy component is used in system head calculation as a basis for establishing entrance losses, losses in valves and fittings, losses at other sudden enlargements, and exit losses by applying the appropriate resistance coefficient, K, to the velocity term. Now, notice that question 12 gives specific losses associated with friction. 3 feet of head is lost at the piping entrance, and 1.5 feet per 100 feet is lost due to friction in the pipe. These are the components of friction head, so there's nothing to actually apply a velocity calculation to. By a simple process of elimination, then, the NPSH calculation needed from section 3.7.4 is for available. But even without that process of elimination, it's possible to use critical thought to capture all the necessary information for the solution. Using this simple diagram, all the elements can be determined. This tank is open to the atmosphere, and that atmosphere exerts the force of pressure on the water. The direction of that force is in the direction of the flow. The pull of gravity due to altitude exerts a force on the water, also in the direction of the flow. The squeeze of the water going into this fitting exerts the force of friction on the water. But it's a slowing, inhibiting force, so the direction is in opposition to the atmosphere and altitude. Likewise, the force of friction within the pipe exerts opposition to the flow. Finally, remember from the ideal gas law, temperature and pressure are linked. The water that's flowing has a temperature, and that temperature is manifested as a pressure, and that pressure pushes against all the boundaries of the flow, increasing friction. So again, the direction of that force is opposed to the flow. 2 forces in the direction of the flow, 3 forces in opposition to the direction of the flow. So the head at this point is a simple matter of adding and subtracting. All values must be converted to feet. Populating with the information from the question, it's only atmospheric pressure and fluid pressure that need this conversion. Table 1.1 in the NCEES Mechanical Reference Handbook gives 1 atmosphere as 33.90 feet of water, and it gives 1 psi as 2.307 feet of water. The pressure of 200 degrees Fahrenheit water is 11.51 psia, as found in the steam tables in section 6.3.1 of the handbook. So, the fluid is at 26.55 feet of water. For a 50-foot length for this pipe, at this friction, there is 0.75 feet of water. The answer is 4.1 feet, option C. To get good at questions like this, you should be able to quickly reference the NCEES Mechanical Reference Handbook to find things like NPSH. You have to be really quick, because you'll still need to decide which one to use once you've found them. Get good at it in the only way possible, by practicing lookups in it. To do this, ExOverZero has a one-of-a-kind drill book for the NCEES Mechanical Reference Handbook. Use the link below to purchase.